Alright, here's an example with a pair of 3x3 matrices, A and B. Each of them is 3x3. And let's multiply them. Now, because they're 3x3, the result is going to be 3x3. And again, I want to really drive home how we find the entries for this. So suppose I wanted to find what number went here. Well, this is in row 3, column 2. This result is the result of taking the third row and the second column of these two matrices and multiplying them together. 0 times 1, 0 times minus 2, 1 times 0. This is 0. Take another one. Say this value right here. Well, this is in the first row, third column. So I would find the result that is that entry by taking the first row, third column. So 2 times 0, that's 0. 1 times minus 1, that's minus 1. 1 times 1 is 0. So this would be another 0. Let's write these things in here. Right. So any one of these entries can be found in any order you want by considering their address. Now let's run through this a little faster. So we'll go across the top. First row, first column, minus 2 plus 3 plus 0 is 1. First row, second column, 2 minus 2 plus 0, that's 0. Second row, second row. Second row, first column, minus 3 plus 3 plus 0, 0. Second row, second column, second row, second column, 3 minus 2 plus 0. Second row, third column, second row, third column, 0 plus minus 1 plus positive 1 is 0. Third row, first column, third row, first column, 0 plus 0 plus 0. Then third row, third column, third row, third column, 0 plus 0 plus 1. So this matrix 1 0 0 0 1 0 0 0 1 is the identity, or say the identity sub 3 is the square matrix identity for 3x3s, is like the number 1, just like in the previous video. So if I take something like A, 2 1 1 3 1 1 0 0 1, and I multiply in any order that I want by the identity matrix, I'll get the same thing back again. So if you were to, and you can see this, look, taking this first row times the first column, these zeros mean we don't count the ones. There are zeros in the second column. The 1 picks up that 1. In the third column, this 1 picks up the last 1. And we just do it again and again and again. If you work this out, and you probably should, you'll see you get the same thing. A times I equals A. And this means, thinking in the context of the previous video, that B is A inverse. Or conversely, A is B inverse. Right? They're both inverses of each other. And you can multiply these two in either order that you want, and you should get this result. So you could try on your own doing B times A. It should equal I. Well, it's a good test to see how you're doing. So hopefully you can see a pattern beginning to form here. You know, the identity matrix for 7x7 matrices would look like this. 1, 2, 3, 4, 5, 6, 7. And then you would just populate this thing with 1s on the diagonal. I haven't mentioned what the diagonal is, but hopefully that's clear from the context. All right. So this thing here is called the main diagonal of any matrix. Diagonal. Right? And then this part is the upper triangle. And this part is the lower triangle. You will hear people talk about upper triangular matrices, lower triangular matrices, and there are also off diagonals. This would be an off diagonal right through here. And so would these. These would be off diagonals. The diagonal ends up being pretty important. We'll see this later with eigenstuff, eigenvalues, and eigenvectors. But square matrices always possess an identity. Some square matrices possess inverses. Some do not. We'll talk about how we know when we get to determinants.